Within the InfoSec community, discussions surrounding aerospace and maritime RF signals are common. Yet North American railroad communications remain largely overlooked. Today we will bridge that gap by exploring the railway OT networks, focusing on the radio protocols and remote systems that keep them running. We begin with the Positive Train Control, or PTC, an advanced command and communications architecture designed to automatically halt the train before critical accidents can occur. Structurally, PTC bridges the gap between locomotives in transit, wayside stations monitoring track conditions, and dispatchers in the back office managing routing and movement authorities. But why is a system like PTC so critical? In 2008, a fatal head-on collision between a commuter train and a freight train in Chatsworth, California, caused by a train engineer missing a red signal, resulted in 25 fatalities and over 100 injuries. This tragedy became the catalyst for a U.S. federal mandate implementing PTC across the rail industry to ensure such an accident could never happen again. The risk, however, is not confined to the past. As recently as 2024, a GO Transit commuter train in Canada passed a stop signal and entered a track occupied by an oncoming train. The crews managed to brake and narrowly avert a disaster, stopping just 500 feet apart. In the wake of this near miss, Canadian regulatory bodies are now actively moving to mandate PTC implementation on key routes and high-speed corridors. With a clear understanding of what's at risk, let's explore the PTC architecture in greater depth, beginning with the onboard locomotive systems. From an operator's perspective, the primary interface is the PTC display unit, positioned in this image to the operator's left. Through this display, the systems communicate critical real-time data including speed restrictions, track authorities, and braking warnings. The information rendered here is processed by the train management computer modules, which is housed in an electrical cabinet located behind the cab. The TMC is the brain of the onboard system. It cross-references real-time location data with movement authorities received from the back office and will actively initiate enforcement braking if the operator fails to respond to a warning. Because the TMC and display unit handle these critical safety functions, they represent primary security targets for research. Naturally, I attempted to acquire a set for my own lab environment. While they do occasionally appear on secondary markets, they are significantly outside a standard research budget, and I doubt a crowdfunding campaign would bridge the gap any faster than it would buy me a top-tier GPU. For now, my dreams of running the world's most over-engineered model train set remain on hold. That said, if anyone happens to have an old TMC collecting dust in a storage locker, my doors are always open for hardware donations. Barring that, you can support this research just as effectively by engaging with its content, leaving your thoughts below, and sharing this with other researchers in the community. The next core pillar of the PTC architecture is the wayside systems. Wayside infrastructure encompasses the diverse array of sensors and telemetry equipment deployed directly along the right-of-way. This includes everything from RF readers used for rolling stock inventory to wheel impact load detectors, machine vision inspection systems, and even the road crossing gates encountered during a daily commute. The local telemetry from these field devices is fed directly into a Wayside Interface Unit, or WIU. The WIUs are located in secure environmental enclosures, commonly referred to in the industry as Wayside Bungalows, as shown here. From these bungalows, the WIUs aggregate and relay critical track status data back to the central back office or directly to oncoming locomotives in real time. While similar to other PLCs, the WIUs are designed to be fail-safe devices handling critical operations such as signaling. Our next stop in the core PTC architecture brings us to the central back office. The back office serves as the nerve center of the network, where dispatchers remotely manage track switching and issue formal movement authorities to en route locomotives. Architecturally, the back office network relies on a proprietary suite of IP-based protocols, which we will dissect in detail in an upcoming video. For now, as a brief aside for the hardware minds watching, it's worth reflecting on the striking similarity between complex railway track topologies and the intricate trace etchings on PCBs. Now that we've mapped out the physical components of the network, we arrive to my favorite layer of the PTC architecture, the wireless communications. While data exchange between these nodes can occur over standard cellular and Wi-Fi networks, a major challenge arises when one rail carrier operates its locomotives on another company's tracks. To ensure seamless interoperability across disparate networks, the industry utilizes the interoperable train control radio, commonly referred to simply as the 220 radio. Operating within the 220 to 222 MHz VHF spectrum, these radios form the backbone of trackside data transport by using a protocol called ITC-net to provide the physical link and network layers. This slide outlines the specific channelization and frequency allocations used to locate the data streams. If you live within range of a rail line, and in the United States you probably are, you can easily receive these RF signals using a standard software-defined radio. In an upcoming video, we will explore the nuances of capturing and demodulating this raw data and the ITC-net. As you see from the technical breakdown, the IETMS columns denote the frequencies allocated for freight operations, while the ACES columns are reserved for passenger rail. These two sectors utilize fundamentally different PTC implementations due to their distinct operational environments and historical signaling foundations. Freight networks rely heavily on GPS to track train positions across massive continent-spanning lines, where the train management computer on board must contain a highly detailed geographic database of every single foot of track, signal, and curve in the country. It cross-references the GPS coordinates against this local database to predict braking curves. These track databases need to be signed, verified, and routinely updated, which introduces a massive data integrity attack surface. Conversely, passenger systems depend on track-embedded transponders and cab signaling infrastructure, which are optimized for high-density, high-speed corridors like the Northeast Corridor. Amtrak serves as a fascinating hybrid case, actively utilizing both architectures depending entirely on the specific territory its trains are traversing. That concludes our fundamental look at the PTC architecture, but the attack surface extends much further. If you achieve physical access to a locomotive's internal cabin, you won't be able to hook into its Ethernet network with a standard RJ45 patch cable. To withstand the harsh vibration and environmental demands of the railway operations, the industry relies heavily on ruggedized M12 circular connectors. Fortunately for researchers, M12 to RJ45 adapters are readily available on the commercial market. The challenge lies in the specifications. You must match the correct gender, pin count, and coding. For high bandwidth data, Rail Ethernet typically utilizes X-coded M12 connectors, not shown here. Some targeted reconnaissance or carrying a comprehensive adapter kit is necessary to interface with a specific locomotive's layout. Beyond the internal network ports, we encounter the AAR 27-pin multi-unit cable, otherwise known as the MU cable. This heavy-duty electrical jumper assembly is the standard form factor used to daisy-chain multiple locomotives or passenger cars together. MU cables handle a variety of both control and communication roles, with different cable types differentiated solely by outer color coding and physical keying to prevent dangerous misconfigurations on the tracks. The primary control cable allows a single lead locomotive to synchronize the traction engines, braking systems, and mechanical functions of all trailing units simultaneously. Interestingly, there's no high-level digital wire protocol running across these lines. Instead, the system utilizes a robust 74-volt DC signal applied directly to specific pins to trigger system actions. The communication variant of the MU cable originally operated on a similar analog principle, with 74-volt DC to manage passenger car operations like automated doors and emergency braking loops, while using variable AC voltages to drive legacy audio lines for onboard PA systems and cabin media distribution. However, in modern passenger transit, the communication lines, and only the communication lines, have evolved to encapsulate Ethernet over train line, routing network traffic through the cars. While the MU cables handle critical signaling between connected locomotives, managing the pneumatic braking system across the entire length of a mile-long freight train requires a different approach. This brings us to the end-of-train device, or ETD, shown here. This device is also more colloquially known in the industry as a FRED, for flashing rear-end device. Mounted directly to the coupler of the very last car, this unit consistently monitors and relays vital telemetry back to the front of the train, including brake pipe air pressure and motion status. From an RF reconnaissance perspective, the continuous data bursts transmitted by these units can be monitored to audit track activity, effectively allowing researchers to detect an approaching train long before it's audibly or visibly present. Crucially, this wireless link is bidirectional. The corresponding head of train device, or HTD, inside the lead locomotive cabin can transmit commands back to the EDT unit to rapidly vent air pressure from the rear of the train, initiating an emergency brake application from both ends simultaneously. Finally, we loop back to the passenger rail infrastructure mentioned earlier to look at the embedded transponders themselves. These ruggedized track-bound transponders are mounted directly between the rails to provide commuter and high-speed rail systems with high-definition, localized positioning data. As a locomotive passes over these fixed units, an onboard antenna energizes the transponder via RF coupling, prompting it to transmit precise location coordinates, upcoming track geometry, and speed restrictions back to the cabin. This high-fidelity ground truth complements GPS, ensuring absolute situational awareness, even in dense urban canyons or subterranean transit tunnels. I hope this glimpse into railway OT networks has provided some valuable insight into a fascinating yet often overlooked layer of our critical infrastructure. If you would like to connect or follow my ongoing security research, you can find all my social handles listed here on the screen. If you enjoyed this presentation and want to see more content like it, please take a moment to leave a comment below with your thoughts and share the video with a colleague or friend who shares an interest in radio and industrial security networks. Thank you for watching.